Welcome to this explainer. Today, we're going to bridge a totally mind-bending gap. We're going to discover how the exact same physics used to light up the dark, microscopic caverns of the human body is also unlocking the very edge of the universe. It's an absolutely incredible story of how mastering light allows us to see both the impossibly small and the unfathomably distant. So picture two radically different scenarios for a second. On the one hand, you have a microscopic tissue change, say a life-threatening stomach ulcer, being treated in a rural clinic in India, and on the other hand, an ancient galaxy sitting 10 billion light-years away from Earth, completely shrouded in the darkness of deep space. I know, it sounds like a trick question, right? Medicine and astrophysics. A rural clinic and the literal cosmos. But what do these two wildly different scenarios actually have in common? Well, the answer is optical precision. Both of these frontiers were completely inaccessible, just totally dark to us, until we figured out how to manipulate the fundamental behavior of light. Let's kick things off with Section 1, the diagnostic black box. We'll start small, exploring a historical medical crisis where doctors faced a literal diagnostic black box. Before modern optical tools came along, the human gut was an impenetrable mystery. Doctors couldn't just look at a stomach ulcer or spot a tiny tumor. If a patient came in with severe internal pain, surgeons had to perform an exploratory laparotomy. That essentially meant literally cutting a patient open just to look inside. Think about the reality of that for a moment. This blind surgery approach was a nightmare. It led to high infection rates, massive traumatic scarring, and incredibly long, painful recoveries. The medical stakes were absolutely huge, and the urgency to find a better way was real. Now you might be wondering, hey, why not just use X-rays to look inside? Well, this perfectly highlights the inherent limitation of how light waves behave. Sure, X-rays penetrate deep into soft tissue, but they only provide dense shadow graphs. You get the rough outline of a problem, not the detailed picture. Visible light, on the other hand, gives us incredible spatial resolution. It can show you the exact texture and color of a single cell. The one major problem, visible light simply can't pass through human skin. Which brings us right to Section 2, the endoscopic revolution. Let's look at how finding a way to pipe visible light directly into the human body without major surgery completely solved this crisis. The massive breakthrough here comes down to a physics principle called total internal reflection, or TIR. Think of it like trapping light inside a flexible tube. By using a glass core wrapped in a specific outer cladding layer, the physics literally changes. Instead of the light passing through the glass and just bleeding out into the body, it hits the boundary at a specific critical angle and bounces back inward, exactly like a mirror. This simple but profound secret meant we could finally send visible light traveling around the tightly curved, pitch-dark tunnels of the human body without losing the beam. But getting a beam of light in is really only half the battle. You also have to consider numerical aperture. In physics, this dictates the essential light-gathering power of your instrument. When you're dealing with the absolute pitch-black environment of the human gut, you need to collect enough of that bouncing reflected light to actually see what you're looking at. The math calculates the exact angles required to capture as much of that scattered light as humanly possible. So a higher numerical aperture directly translates to a massively brighter, clearer image for the surgeon. This was a total paradigm shift. Imagine being a doctor who is used to relying on feeling around in the dark or performing dangerous exploratory surgeries. Now, suddenly, you can pipe a brilliantly bright, high-definition image right back out of the body in real time. It completely turned blind surgical guesswork into pinpoint optical precision. Engineers actually conquered this in 3 brilliant phases. Phase 1 was illuminating the dark, using those trapped bouncing light beams we just talked about. Phase 2 was mapping the image perfectly using coherent fiber bundles. So a fiber at the top left in the patient's stomach stayed at the exact top left on the doctor's screen, so pixels never got jumbled. And finally, Phase 3 brought us narrowband imaging. By filtering for very specific blue and green wavelengths that blood vessels rapidly absorb, doctors could suddenly spot microscopic, precancerous lesions that were totally invisible to the naked eye. The real-world impact of this optics bridge? Absolutely staggering. In places like India, this technology transformed grueling, highly dangerous 10-day hospital stays into simple routine daycare procedures. And because the image is converted from an optical signal to a digital one via a tiny sensor at the tip, it fully unlocked telemedicine. Think about the gravity of that. A top-tier specialist sitting in New Delhi can now view a high-resolution, life-saving procedure happening in a rural clinic hundreds of miles away, in real time. Okay, let's move to Section 3, Hubble's multi-billion-dollar blur. Prepare for some serious scale whiplash as we pivot from the microscopic interior of the human gut to the vast, incomprehensible expanse of outer space. Back in 1990, the Hubble Space Telescope was launched into orbit. Sitting high above the Earth's distorting atmosphere, it was supposed to be humanity's ultimate perfect eye on the cosmos. But when the very first images were beamed back to NASA, they were frustratingly milky and severely blurred. I mean, it was an absolute devastation. Billions of dollars spent, decades of engineering, and the perfect eye was practically blind. The telescope essentially had nearsightedness on a galactic scale. Forensic engineers immediately scrambled to figure out what went wrong. They tracked this massive, multi-billion-dollar myopia down to the telescope's huge 2.4-meter primary mirror. Deep in the polishing data, they discovered an unbelievably tiny manufacturing error on the very edge of the mirror. The deviation measured exactly 2.2 microns. To put that tiny 2.2 micron number into perspective, that is about 1/50th the thickness of a single human hair. It was a flaw completely invisible to the human eye. But in the highly sensitive world of ray optics, a 2.2 micron deviation is an absolute canyon of an error. When you're trying to capture light from galaxies billions of light years away, even a microscopic bump acts like a massive brick wall. This tiny error caused what optical physicists call spherical aberration. Basically, imagine light hitting a perfectly curved mirror. You want all those individual rays of light to bounce back and meet at one single perfect point to create a sharp image. But because the outer edge of Hubble's mirror was polished just slightly too flat, the physics totally broke down. Light hitting the center focused exactly where it was supposed to, while light hitting those flat edges focused somewhere else entirely. The result? Because there was no single focal point converging in one spot, the telescope's camera could never actually focus properly. It created what's literally known in optics as a massive circle of confusion. All the incoming starlight just smeared together. So instead of a razor-sharp, crystal-clear point of ancient light, Hubble was looking at a hazy, blurry universe. Which leads us to Section 4, Spectacles for a Telescope. NASA had to figure out a fix, and fast. Obviously, NASA couldn't just bring a massive space telescope back down to Earth, put it in a lab, and repolish the mirror. So, they used the brilliant principle of optical compensation. Using complex inverse calculations, scientists figured out the exact opposite of the mirror's error. They then built CoStar, essentially a pair of highly sophisticated corrective spectacles for the telescope. Think of it like wearing glasses to fix an astigmatism. By inserting tiny new mirrors with the exact opposite flaw in front of the camera, the two errors perfectly canceled each other out. Total optical aberration equaled exactly 0, and Hubble's vision suddenly became breathtakingly perfect. Moving on to Section 5, the James Webb evolution. Decades later, NASA wanted to make sure they never repeated a Hubble-scale mistake. To do it, they took a completely new approach with the James Webb Space Telescope. The evolution here is just astounding. While Hubble relied on a fixed-ray optics geometry, a single massive mirror that eventually needed external corrective glasses, JWST uses real-time wavefront sensing. Its mirror isn't one giant rigid piece. Instead, it's made of 18 separate, incredibly lightweight segments. And the real genius? These segments use microscopic motors called actuators to actively adjust themselves out in space, correcting their own alignment based on complex light interference patterns. Because JWST looks at extremely long infrared wavelengths to peer through cosmic dust, it constantly battles the diffraction limit. To overcome this fundamental limit of physics and maintain ultra-high resolution, it requires a massive 6.5-meter mirror diameter. The incredible part is that the tiny actuators on the back of these giant segments align the mirrors to within mere nanometers. That is a level of precision that is actually smaller than the wavelength of the light it's capturing. No way, right? So what should you really take away from this explainer? Well, whether we're spotting a microscopic, life-threatening stomach ulcer in a remote clinic or capturing the faintly glowing very first stars born right after the Big Bang, precision in optics is a requirement, not an option. We've bridged the seemingly impossible gap between human medicine and deep space astronomy using the exact same fundamental principles of light. It's an absolute testament to human ingenuity, and it really leaves you wondering, with our ever-evolving mastery of the optical world, what will the light reveal next?